Hi, I'm Herbert Gross. Welcome to lecture number 11 in Gateways to Algebra, where today we're going to talk about applying the rules of the game of math to algebra, okay? Now, what we're going to do is go back to the same things we were doing before and look at some of the things. Remember, I think it was the very end of our first lecture where I went through the beginning of algebra and I said something like, if this is all there is to algebra, why is it going to take a year or 2 years to learn what there is to know, etc., etc.? Well, we're going to take a little bit of a look at this now from different perspectives and start to see what's happening. Let's go back to pick a number, because it dawned on me that pick a number seems kind of childish. Little kids do that. So we're going to call it PAN from now on, pick a number. And that way, if somebody walks through, they'll think it's some prestigious type of computer language or something. But PAN will stand for pick a number, and WTA will stand for write the answer. So PAN will be a clue that we're talking about the input, and WTA will be a clue that we're talking about the output. Now let's just string a few steps together. We say pick a number, multiply by 2, add 3, multiply by 6, add 2, divide by 4, add 4, divide by 3, write the answer. And you begin to see how tedious this is becoming. And by the way, do you see the difference between difficult and tedious? These steps are not difficult, but there's a lot of them, and I could write a couple of hundred more if the problem was complicated enough. But let's just pick a number like 7 and see what happens over here. We start with 7, multiply by 2 gives us 14, add 3 gives us 17, multiply by 6 gives us 102, add 2 gives us 104, divide by 4 gives us 26, we add 4 gives us 30, we divide by 3 gives us 10, and so when we write the answer, if we start with 7, we got 10. And by the way, again, notice these are all constants. In other words, whatever number I pick, I'm still going to do these same steps. The answers will be different because the number I pick is different. For example, let's just pick another number. Suppose I started with 15. I multiply by 2 gives me 30. I add 3 gives me 33. I multiply by 6 gives me 198. I add 2 gives me 200. I divide by 4 gives me 50. I add 4 gives me 54. I divide by 3 gives me 18. So if I start with 15, the output is 18. Okay? By the way, people start to get curious. They say things like, gee, when he started with 7, he wound up with 10. When he started with 15, he wound up with 18. Goodness, the output seems to be just 3 more than the input. In fact, could I take a guess and just try something? For example, could I say, gee, let me just take a guess over here. I'm going to just guess something. I bet you if the input was 3, the output would be 6. I'm going to just take a guess that every time you do this problem, the output is going to be 3 more than the input. Let's see how that would work over here. I start with 3. I multiply by 2 gives me 6. I add 3 gives me 9. Multiply by 6 gives me 54. Add 2 gives me 56. Divide by 4 gives me 14. Add 4 gives me 18. Divide by 3 gives me 6. Golly, it seems to have worked. Now, by the way, some people may not have noticed this at all. Other people may notice it. Other people may have noticed a different pattern. And you just keep on going. By the way, do you see the problem with this? Let's suppose I believe that when I use this program, every time I have an input, I believe that the output will be 3 more than the input. See, 7 led to 10, 15 led to 18, 3 led to 6. Until I do the next one, can I be sure this is going to happen? Suppose I make 50 predictions, and all 50 of them happen to be right. Is there any guarantee that the 51st time it will be right? You see, if I'm a scientist and I do an experiment 200 times, is there any guarantee until I've done it that it's going to be right on the 201st time? See, suppose somebody says to you, I bet you the world won't be here tomorrow. That's a great bet to take. Because if it's here tomorrow, you win. And if it's not here, there's no one to pay. But when do you collect on that bet? Not until tomorrow. Because until tomorrow, all you have is an educated guess. You see, in the world of science, until an experiment is over, all we have is a hunch. Suppose, for example, that the Lord was to grant us immortality and didn't tell us, how old would you have to be before you knew you were going to live forever? 200, 300, 40 if you smoke a lot? What? No matter how old you are, you have no guarantee till the next day that you're going to be there till the next day. That's called empirical or inductive education. In other words, you look at something and based on what you see, you make a guess. There's nothing wrong with that provided that you realize its limitations. In fact, let me show you a cute little riddle of sorts. It's tricky, but it's meant to illustrate a point. I have a picture in mind. In other words, I have a scheme in mind, and there's a pattern behind these numbers. The numbers are 31, 30, 31, 30, 31, 31, 30, 31, 30, 31, and 31. I want you to look at these, and based on your intuition, based on your ability to deduce empirical evidence, I want you to tell me which number goes in the blank over here. And by the way, you may come up with all kinds of schemes. Remember, I'm telling you, you have to guess what I have in mind. And what I have in mind mustn't be frivolous. It has to be well defined. Most people split into equally between 30 and 31. I mean, very few people actually give me a guess other than 30 or 31. Anybody happen to know what number I'm thinking of? It's 28. And having seen that, do you now know what I'm doing? These are the number of days in a month, starting with March, in a non-leap year. See, April has 30 days, May has 31, June has 30. See, July, August, September, October, November, December, January, February. Now, once I show you once I tell you what my scheme is, everybody will know that this is 28. But just looking at these, it's kind of hard to guess. Oh, there's a whole bunch you can make up this way. I'll just give you another one. I'll put down an O, then 2 T's, 2 F's, 2 S's. What comes next, do you know? It's an E. And what you're doing is you're counting 1, 2, 3, 4, 5, 6, 7, 8. And you're doing what? Writing down the first letter of the word that the number begins with. And by the way, if a person didn't speak English, there'd be no clue as to what you're supposed to do with this. But you see what I'm saying? In other words, just by looking at a pattern is no guarantee that you're going to remember or guess what the next number is supposed to be. So what we do, and by the way, the reason I'm leading up to all of this is to show you the power of the game of algebra. What we're going to do now is not guess anymore. What we're going to say is, why fool around with starting with 3 or 4 or 7 and seeing what's happening? Let's start with any old input, which we'll call x. And let's see what the output is going to look like in terms of x. What's the first step say? It says multiply by 2. Well, when you multiply x by 2, you get 2x. The next step says what? Add 3. Well, we already have 2x, and now we're adding 3. And by the way, notice I don't have to put grouping symbols over here. I just did that for effect, because it says what? When there are no grouping symbols, multiplication is done before addition, so we would have multiplied the 2 by the x before we added the 3 anyway. The next step says what? Multiply by 6. So the 2x plus 3, that whole number has to be multiplied by 6. Let's do that. Now, what rule applies here? Isn't the 6 multiplying the sum of 2 numbers? And wasn't that our rule for combining multiplication and addition in the same problem, the distributive property? What's going to happen here? The 6 is going to have to multiply the 2x. Well, if you take 2x 6 times, that's 12x. And the 6 also has to multiply the 3. 6 times 3 is 18. So now you have what? 12x plus 18. What are you going to do to that? You have the 12x plus 18, and now you have to add 2. Well, doesn't my associative property tell me that I can take the 12x, leave that alone, regroup this so I'm adding, remember we said that in an addition problem, you don't need the parentheses? I can now do what? Leave the 12x alone and add the 18 and the 2. That would give me 20. By the way, I can't add the 20 and the 12 because the 12 is modifying x and the 20 isn't. You see, 12 plus 20 would be 32. 12x plus 20x would be 32x. But 12x plus 20 is just 12x plus 20. It's sort of like when you have a report card with 3 A's and 2 A's, that would be 5 A's. 3 B's and 2 B's would be 5 B's. But if you have 3 A's and 2 B's, you don't call it 5 A B's. You just have to leave it as 3 A's and 2 B's. Anyway, the next step is what? Divide by 4. But we agreed in this course that dividing by 4 is the same as what? Multiplying by 1/4. And by the way, if this looks a little bit tedious, that's fine. I'm just trying to illustrate what's going on here. Now, is 1/4 a number? Yes. Is it multiplying the sum of two numbers? Yes. Therefore, can I use the distributive property again? Yes. I can multiply the 1/4 by the 12x. The 1/4 times 12 gives me 3. The 3 times x gives me 3x. Okay? 1/4 times 20, 1/4 of 20 is 5. That gives me 3x plus 5. What do I do in the next step? I add 4. I don't need the parentheses because it's an addition problem. The 5 and the 4 gives me 9. Again, I can't combine the 9 and the 3 because the 3 is modifying x and the 9 isn't. The next step says what? Divide by 3. That's the same as multiplying by 1/3. I use the distributive property again. The 1/3 has to multiply the 3x. 1/3 times 3 is... In fact, by the way, if somebody wants to play the game more rigorously here, see, when the 1/3 multiplies the 3x, the first thing we say is what? You can shift the parentheses so that the 1/3 and the 3 are grouped together. 1/3 multiplied by 3, that's the multiplicative inverse property. That's 1 times x. And 1 times x is the same as x. In other words, if a person challenged me when I said 1/3 of 3 is 1 and 1 times x is x, I could say, well, here's how it works step by step using my rules. And what's 1/3 times 9? 1/3 of 9 is 3. Now let's look what we did. Here's the input. What's the output? The input was x. The output, no matter what x stands for, is what? X plus 3. How much does x plus 3 exceed x by? It exceeds it by 3 units. In other words, now we've shown that what? All these steps combined reduce to simply what? All these steps could have been replaced by what simple step? Start with x and add 3. Let me just see if I can show you something here. Look at these two programs. The first program says pick a number, and watch these 7 steps. It says multiply by 2, add 3, multiply by 6, add 2, divide by 4, add 4, divide by 3, okay, and write the answer. The second program says pick a number, add 3, and write the answer. Is it clear that the second program is clearly simpler than the first program? Well, any program with just 1 step is simpler than a program with 7 steps. But here's the beauty. It's that this 1 step is equivalent to all 7 of these. It's not just that this is simpler, it's that it says exactly the same thing. For example, let's suppose, remember when we started with 7, the answer was 10? Well, that tells us that right away. Suppose somebody told me in this problem over here that the answer was supposed to be, or we'll just make something up, 11. How would I have found out what the input was using this method? I would have said, okay, to undo dividing by 3, I'm going to multiply by 3. To undo adding 4, I'm going to subtract 4. To undo dividing by 4, I'm going to multiply by 4. To undo adding 2, I'm going to subtract 2. To undo multiplying by 6, I'm going to divide by 6. To undo adding 3, I'm going to subtract 3. And to undo multiplying by 2, I'm going to divide by 2. And do I get that the input must have been 8? But I'm saying what? These two programs are equivalent. So instead of going through all of this, why don't I just say what would have happened here if the output was 11? To undo adding 3, I just subtract 3, and there's the answer right away. In other words, any problem that involves program 1 can be replaced by an equivalent problem involving program 2. And think of these as being movable parts. The more steps there are, the more chance there is to make a careless mistake. Look how neat this is. Hardly any places to make a careless mistake here. See, and we can do a lot of things like this. Let's just look at a couple of more programs just to get the idea over here. Here's one that gave us trouble before. Let's start with an input, multiply by 3, add 2, multiply by 4, add the input, and the output turns out to be 99. what number did we start with. Okay? See, how would we do this based on my first lecture? You'd say, okay, since the output was 99, we want to invert each of these steps. So what are we going to do over here? To undo adding the input, what we're going to do? We're going to subtract the input. The problem is we're trying to find the input. How can we subtract the input if we don't even know what it is? You see what's happened over here? This makes sense. By the way, suppose I started with 1. I multiply by 3, gives me 3. I add 2, gives me 5. I multiply by 4, gives me 20. Now it says add the input. 20 plus 1 is 21. So if I start with 1, the answer is 21. You see, I have no trouble following these steps. In fact, I've just found out that what? 1 is too small to be the right answer because the output would be 21. I want the output to be 99. But you see, the problem is I seem to be stuck trying to use the logic. But here's what I do. I say, let's see if the game will help me here. I'm starting with x. What's the first thing I did? I multiplied by 3. What's the next thing I did? I added 2. What's the next thing I did? I multiplied by 4. But this is now the distributive property. The 4 has to multiply the 3x. That gives me 12x. The 4 has to multiply the 2. That gives me 8. And what's the next thing I have to do? I have to add the input. What is the input? It's x. Well, let's see what I can do over here. Oh my God, there's a 12 in front of the x. There's nothing in front of this x. But don't I have a rule that says that I can put a 1 in front here? Don't we have the rule of the multiplicative identity that 1 times a number gives me back that same number? So this becomes what? 12x plus 8 plus 1x. Can I now regroup this by the associative and commutative properties? Write the thing this way. And now isn't 12x plus 1x 13x? And how do you read this program now? It says start with x. Let's just read this. It says input x. Then you do what? You multiply before you add. Multiply by 13. Then what do you do? Add 8. And then you can put down the output. Doesn't this program here look much simpler than this program over here? But let's see what happens. Since these two programs are equivalent, they don't look alike, but they're equivalent. Whatever input will give me 99 here, it should also do it here. But does this one work better for me? Let's invert this one. The first step we want to do is what? Undo adding 8. So we subtract 8. 8 from 99 is 91. We next want to undo multiplying by 13, so we divide by 13. 91 divided by 13 is 7. Therefore, the input must have been 7. Well, let's see if it works. If the input was 7, 7 times 3 is 21. 21, we'll put it down so we don't forget. 21 plus 2 is 23. 23 times 4 is 92. Add the input, 92 and 7 is 99, and lo and behold, we have it. And here, by the way, is one of the most beautiful applications of math. For the people who know they need algebra, that's fine. But for the person who says, I'm not going to go into math, I don't need to know this, I just want to be good in being able to understand life, etc., etc. What I want you to see is the power of paraphrasing. By using the rules of the game, what were we just able to do? We were able to take a problem we couldn't solve and reduce it to a simpler but equivalent problem that we could solve. And this is the history of humankind. That we take new problems we've never seen before, and what does our logical mind allow us to do? To break them down into a sequence of simpler problems, each of which was solvable before. And we then string these together to find the answer. You see, to be able to paraphrase transcends mathematics. Anybody can change the wording, but to change the wording without changing the meaning, that's a skill. That's an art form. And algebra helps you develop this. So that even if you see no practical use for algebra, even if you don't see, why would anybody ever say, pick a number, multiply by 3, add 2, multiply by 4, add the input, what's the output? The beauty is what? That whole complicated recipe could be replaced by what? Start with a number, multiply by 13, and add 8. I think we have time for one more. Let's take a look at this one. It says, pick a number, input, okay, x, subtract it from 15, multiply by 2, subtract it from 40, divide that answer by 2, subtract 4 from that answer, and then write the answer. Now this thing makes sense. Let's just take the number 4, for example. Start with 4, subtract it from 15, and by the way, notice the reading comprehension. The 4 is being subtracted from the 15. Don't confuse it with subtracting 15 from 4. It's being subtracted from 15. 4 from 15 happens to be 11. Multiplied by 2 gives me 22. Subtract the 22 from the 40. See, I'm taking the 22 away from the 40. That's going to give me 18. Divide the 18 by 2 gives me 9. Subtract 4, okay, gives me 5. And therefore, if I started with 4, the answer is going to be 5. Now, I think I could work backwards over here, starting, let's do another one. I say, what if the output was 14? What would the input have had to have been? Now, I can work through this and then have to be careful about how do I undo subtracting from 40 and things like that. But let me show you, again, the power of the algebra just with this one concluding example. I start with x. See, just like when I started with 4, I subtracted that from 15. Now I'm going to subtract the x from the 15. That's 15 minus x. But remember, subtracting is adding the opposite. Okay, so that's 15 plus the opposite of x. Now I'm going to multiply by 2. The 2 times the 15 gives me 30. The 2 times the negative x gives me negative 2x. Now what do? I'm going to take that number and subtract that from 40. But to subtract, let's see if we can do this. To subtract means what? Add the opposite. And notice I put the minus sign, the negative sign, in front of the parentheses because it's the whole thing in parentheses that's being subtracted. Now, I'm stuck here because I don't usually have just a negative sign in front of the parentheses. There's usually a number over here. But didn't we always say that putting a 1 in front of something doesn't change it? In other words, one way of taking the opposite of a number is doing what? Multiplying it by negative 1. So we have the 40. The negative 1 multiplies the 30 to give me negative 30. Negative 1 times negative 2x is positive 2x. 40 plus negative 30 is 10. So this is 10 plus 2x. Okay. Now the next step says what? Divide by 2. That means multiply by a half. A half of 10 is 5. A half times 2x is x. The next step says what? Subtract 4. But subtracting 4 is the same as adding negative 4. I can add in any order I want. So here's the x, and the 5 plus the negative 4 gives me positive 1. And lo and behold, what this tells me is this whole mess over here can be replaced by what simple command? Pick a number and add 1. Look over here. What number did we start with over here? We started with 4. What was our answer? 5. After all this work, all we ever did was what? Wind up with 1 more than we started with. And look what the algebraic game told us. It said you could have expected that. In fact, if I now apply this, you see, if x plus 1 is 14, if the output is 1 more than the input over here better be 13. And let's check to see if it works. 13 from 15 is 2. 2 times 2 is 4. Subtract 4 from 40 gives you 36. Divide 36 by 2 gives you 18. Subtract 4 from 18 gives you 14. And lo and behold, you do have the answer. Are you beginning to see now the power of the algebraic approach? It doesn't mean that we couldn't have done these problems otherwise. We could have used trial and error. We could have used other tedious things. But do you begin to see the power of logical thought? Do you begin to see how by using logic we can take problems that would be tedious and possibly even impossible to do other ways and find a method for solving them not only accurately but having proof that it has to be that way? We're going to continue with this for the entire rest of the course in one form or another, and we're going to apply what we did today next time to a very special kind of relationship called a linear relationship. So if you really want to know what a linear relationship is, come next time. And until then, have fun, study hard, stay young.